So I kindly request Professor Das to deliver his talk. Thank you.
I'll be talking of biomicrofluidics. I came to microfluidics as a mechanical engineer, heat transfer, fluid mechanics. Everybody was talking of micro, nano. So I got into microfluidics. But then bio was the farthest I could think about, because last time I studied biology was in 1978, and the very next was 2007, 30 years kind of a difference. The only connection I had with biology was my daughter was studying medicine, and father and daughter always has got this leg pulling thing, and I used to tell her, this is not science. Anything which doesn't have mathematics is not science. And she used to tell, you are alive because of this science. And so this was going on. But that's the time I happened to be at MIT for a year. And at MIT, I was surprised. Forget about chemical engineering, where 90% people were working on bio. Even in mechanical engineering department, more than 50% people were doing bio. So I decided that I will be doing something with bio. So I started reading a molecular biology book by Lodish. And I could read 1 page a day, because every line I was getting stuck with something, with some term. So I said, no, things won't work. So within this turmoil, one day, this happened. In MIT coffee shop, where you enter the staircase and you have a coffee shop at the corner. So on a very busy time in the morning, I was not finding seat, and I got a seat next to an old person with beard, and he said, you can take it, one seat is vacant. And we started talking, and he said, what would you like to do? I said, I want to do bio, but I'm not able to make progress, and I'm a heat transfer man, so I don't know how thermal engineering can be put into bio. The person, of course, didn't disclose his identity, and he said, you can do one thing. Eric is taking a undergraduate course with 500 students. You can be there. Eric Lander. So I said, very good. I went there, and I found, Eric Lander, with a background of mathematics, he has become biologist. So he was teaching biology like mathematics, so it was easy for me. But what was more important, the person was saying, you are talking of thermal. In my life, almost whole life, I have worked with an organism called C. elegans, which finds out the thermal gradient and move. Now, as a heat transfer fluid mechanics man, the moment somebody says gradient, I am very excited, because viscosity is because of a gradient, heat transfer, Fourier law is because of a gradient. So I looked at gradient. So what I started doing is I started looking at literature. Now the thing is, the person invited me for a discussion on that, and it came out that his name is Bob Horowitz, who invented or discovered apoptosis and got a Nobel Prize in 2002. I didn't know that. I mean, even when he said Bob Horowitz, I am so ignorant about biology that I didn't understand that he is a Nobel laureate. I said, Bob, yeah, maybe some Bob Horowitz. So anyway, so after that, I started looking at literature. And what I found was interesting, that within our guts, for example, in our intestine and all that, stomach, intestine, if you see oxygen level, there is a gradient. And if you look at pH level, there is another gradient. And the microbial loads, they are in one direction or other. It's not that everywhere, suppose our inherent microbial, the bacteria which stay within our bodies, they are not uniformly distributed, but they do migrate from one side to another side. And naturally, I thought, since these gradients are there, do they have a role in this migration? So this is the question which struck me. And then I found there are other things as well, because some of these bacteria are anaerobic bacteria. So they won't go to the oxygen level. They will go away from the oxygen level, direction of oxygen concentration, higher oxygen concentration. On the other hand, there are pathogens which move towards oxygen. So there are such cases also within our body. And that also changes with the drug. For example, there is a pathogen and there is a drug to kill the pathogen, but the pathogen, the drug itself creates a gradient, and then that also regulates the migration of pathogens. So when I looked at it, I thought, oh, that's great. But the problem is this, that this is all known. People might not have done very detailed study, but still people know that, yeah, they do migrate in the directions of these chemicals. What is new? The new is, again, it was ringing to me, I must bring heat transfer somewhere. So what I did is, before that, another thing I looked at, which is many of the speakers in the morning said, that's about the fluid flow. Fluid flow always creates the shear within the body. And interesting enough, in our body, there are vessels for fluids, blood or other things, blood, air, and everything, of various dimensions, including the porous media inside your bone marrow. And the pressure drop levels are very different, and stress levels are also very different. So naturally, even the stress gradient, pressure gradient, will also have definitely some effect. So I started looking at it, but then what I did was my collaborator with whom I was working, Professor Roger Cam, I went to him and said, Roger, I want to find out what is the effect of thermal gradient on this, the migration of the cells and all that. The response was very lukewarm. Roger said, the biological people, they think everything is at body temperature 37 degree. Their chemical gradient is fine, they understand. But thermal, they will say everything is at body temperature 37 degree. How does it matter what gradient? I didn't give up. Roger was going for a conference somewhere. I looked for literature and I found a Nature paper in which it is said that the sperms, when they swim through the vaginal passage and go to the egg, the sperms move in the direction of temperature gradient. There is a 3 to 4 degree temperature difference. And the sperms, they find out like heat sink missile, they go in the direction of that temperature gradient. That was the paper. It's a small paper, 2.5 page paper. So when I looked at this, I said, okay, found something which moves in the direction of temperature gradient. When he came back from the conference, I said, this is what I got. But he came out with even more surprise. He said, I talked to many people in the conference, and people recognize that there are temperature gradients within the body, but nobody has worked on that. So being a heat transfer engineer, and my primary, I started my career with heat exchangers. So what I did, I designed a microfluidic device in which, while making, I put 2 tubes, heat exchanger. One connected to the hot circuit, one connected to the cold circuit. This was my simulation, temperature simulation we did. And then we found out with a thermal camera what is the temperature gradient on the other surface, other side, what it is created. We found that our computed and the measured temperature gradients are almost exact. So with that, we created this microfluidic device with inlets, outlets, hot water, cold water, etc. And we put cells, cancer cells, breast cancer cells. And we found that, yes, they do migrate in one direction or other, depending on temperature gradient. So that was the thing that was beginning for me. But then I got into another work there itself with another group. They were not doing anything with microfluidics. This is the group of Professor Sangeeta Bhatia, one of the, I think, editors of Lab on Chip. So what I was doing is injecting gold nanorods into tumors to increase its absorptivity and then ablating the tumor with the help of a laser. That is what I was doing. So we were injecting, these are the solutions, this is the scanning, and then we took up this portion, did a numerical analysis, simulation, found out the temperature profile, and then took the surface temperature and measured, matched it. Now this was our simulation. This was the exact, this is without the gold nanorods, this is without the gold nanorod, and this is with the gold nanorods. Because gold nanorods, increases the absorptivity. Otherwise, the scattering coefficient of cancer tumor cells are much more. Scattering coefficient is 500 per meter, and absorption coefficient is only 40 per meter. So, whereas these nanoparticles of gold rods have got 50 to 60,000 per meter. And so, if we can inject some micrograms of it, the absorptivity increases, then the heat stays with the tumor, it doesn't dissipate into the healthy tissues around. And so that's exactly what we did, and we found out our experiment was this and our simulation was this, so we could do this. Now, this has got nothing to do with that temperature gradient, but what I realized here, that there are too many things. The blood is moving. If you put the drugs are moving because chemotherapy is done at the same time. So drugs are moving, blood is moving, and heat is moving. How do they interact? It's not, if I do a chemotaxis study, how the organisms or cells within the body move under temperature gradient, that's one thing. But temperature gradient and a chemical gradient, another thing. Temperature gradient and two chemical gradients, another thing. Along with that, a stress gradient. That's what exactly happens. Now, this is something you can study in microfluidic devices beautifully. And so, I came back, we got a project from DBT, Department of Biotechnology, and a student joined who is now my postdoctoral scholar, Dr. Nithya. She started working on that. We brought this device. And you can look at this device. We created a channel. We had, this is the chemo effector, this is the buffer. And chemo effector means we can use both. We used one attractor, one repeller, both of them. So I did it, and then we put the cells here to find out where the cells move. But this is the work with, you can see, this is the work with only chemotaxis, chemical gradient. And we found out that with chemical diffusing this way and creating a gradient within the channel, how the cells move. Okay? This was the simulation for chemicals. This was our experimental setup. This was the real one. You can see the channels, and this is the glass plate on which we put it and so on. After this, we put a dextran, red, to find out whatever chemical gradient we got, whether this is the one which we predicted, and they were quite close. So we said, okay, fine, our computational model is fine. We can go ahead. And then we put the cells. And we found out that, whatever is expected, the inhibitor, which is nickel sulfate, which inhibits, they are throwing away the cells on the other directions, whereas the attractor, which is sorbitol, which is taking the cells in the direction of chemicals. This is what is expected. There's no big surprise here. But we could quantify that one through these studies. We could quantify what is the rate of migration. But what we did next was exactly the same thing. On the same device, a thermal gradient. This was our device with two tubes. And again, we found out the temperature gradient, we matched, and then we put cells. And we found out one thing. One is, what is the migration of the cells? And second, along with the cells, if we put gold nanoparticles, what happens? Because that was our intention. If there are gold nanoparticles, what will happen? And what we found is that migration almost stops. At least it reduces and almost stops if there are gold nanoparticles. Now, this can be because of various things. It can be because of interaction of the gold particles with the cells. It can be because of the temperature equalization of the cell, and so on. Because gold nanoparticle, definitely they increases the conductivity of the fluid, effective conductivity. So, now we designed an experiment with both the gradients. Now, if there are both gradients, there can be 4 cases. There can be parallel or counter. That means the thermal gradient drives one way, chemical gradients drives the same way. This is possible. Or thermal gradient drives one way, and the chemical gradient drives the opposite way. What will happen if it is opposing? And this can also be two cases, because the chemical gradient can be done with the help of inhibitor or attractor. So 4 different combinations are possible. So this is opposing gradients, although the because it is chemoattractant, and this is thermal gradient. Whereas if you go to the same configuration, it becomes parallel gradients, because this is chemorepellent. So there can be 4 possible cases, and we did experiments with that. So we have a chemical gradient, we have a thermal gradient, they are aiding each other, they are opposing each other with an attractive chemical and with a repelling chemical. All this we did, very complicated experimental setup. And please understand, this whole thing, when we put the cells, it has to be placed inside a CO2 incubator. It's not that we can do the experiment outside, because it has to be there for days together. And so that's what we did. And what we found is very, very interesting. Let's take this case. This is initially, after an hour, because it is repelling from this side or this side, thermal repels from this side, and chemical repels from this side. So the cells come in the middle first. But in the long run, it goes one way only. And that is decided by the chemical gradient. With further experiments on various chemical gradients, what we found out is this conclusion, that the cell migration direction is decided by the chemical gradient, but the rate is decided by the thermal gradient. If the thermal gradient is in the opposite direction, it will migrate, still migrate in the same direction as chemical, but the rate of migration will decrease. So this is what we found there. Now, these were chemical versus thermal. We were trying to do only on shear. And 2 cases we took. One is, again, the mesenchymal stem cells, with Professor Biswas told in the morning. And we took the other one, which is the cancer cells for metastasis. So in both the cases, we looked at that, what are the mechanotransduction. Mechanotransduction basically means under mechanical, forces, what is the change in the biological system which takes place when they move. Now, this change may not be direct. It may not be directly because of the stress. It can be that the stress induces something, some chemical to come out, some chemical to attach, some chemical to detach, etc., etc. It can go into that chemical or biological, effects, and then that manifests itself as an effect. So that is what is, many things happen at the cell surface level, sometimes inside cell. So that is what is mechanotransduction. And what we decided, that we will see what is the effect of pressure. Because as I have said, within our body, we have got large vessel, aortas. We have got smaller vessels. We have got capillaries. We have got porous medium through which fluid flow. And in every case, the pressures are widely different. So can we have one device in which we will put many pressure differences and then put the cells and find out what happens? So we designed one device which we called logarithmic pressure device. And what is logarithmic? Actually, by optimizing the pressures, we designed channels in which, at the same time when fluid flows, there are 4 channels in which 4 orders of magnitude pressure difference is there. One is 0.01 Pascal, one is 0.1 Pascal, one is 1 Pascal, and one is 10 Pascal. All in the same device, just by changing the design. That's what we did. And then, we did again simulation. This is the one that we fabricated. In fact, that time we fabricated using micro fabrication techniques, standard micro fabrication technique. Today we make the same device with additive manufacturing, 3D printing. So we have done it, and we've tested, and we found out that the kind of pressure we wanted, we got it. And at different flow rates. In fact, what we found that flow rates at that level doesn't have much of a effect on that. But definitely chamber 1, chamber 2, chamber 3, chamber 4 are 4 orders of magnitude, you can see. And so this was our experimental setup in which we put that one, and we wanted to find out what kind of response we get from mesenchymal folds. So we took rat bone marrow mesenchymal stem cells. This was all about, after the first stage of flow, we wanted to see how is the cell attachment with and without silane coating on the cell. And after that, we found out after 4 days, we took only silane coated because that happens to be better than the other one. And we looked at cell alignment, and we found in terms of proliferation, the pressure has got tremendous effect. And in fact, the 2 cases here we have used, one is a steady flow and other is an intermittent flow. And we found that the intermittent flow is better in terms of proliferation rather than and it makes sense also because even in the body, the flow is mostly intermittent. It's a peristaltic kind of flowing. So that's what in 4 chambers with steady and intermittent flow we found out, and we came to the conclusion that the proliferation calculations done through the image processing, etc., tells that cells prefer lower shear stress and intermittent flow for proliferations. That's what was the conclusion. So the next one, we didn't stop only at proliferation or attachment. We also look at gene expressions. Because, at the end of the day, how the cells will, even if cancer cells migrate, how it will behave. In fact, whenever there is cancer, we know, all of us know, whenever there is cancer, there is metastasis. But metastasis doesn't mean that the other organ will be affected. Always it doesn't mean. It may go, the cells migrate from one location to another organ, and quite often they sit there for the rest of the life of the person. Nothing happens. They start you don't even know that the cancer has metastasized. Nobody knows till today exactly under what condition they start proliferating again. So that's why this is a very tricky thing. So we should not carry out studies only on the mechanotransductions, but also the gene expressions. These are important. And that's why we carried out PCR and ALP, alkaline phosphatase. Alkaline phosphatase is something which is connected directly to this, kind of metastatic cancers. This is in your prostate cancer, right? It's metastatic prostate cancers are actually characterized by this, what is called the ALP. So we carried out all these chemical and mechanical cues, and through that one, we could find out what are the gene expressions of different kind of pressures. Under different kinds of pressure, 4 orders of magnitude of pressure, whether the gene expression of one type of pressure is more or less. And the metastasis, everybody knows, as Professor Biswas in the morning said, there are 2 or 3 stages. One is intravasation, where from cancer they detach, they convert into mesenchymal cells, they get into the bloodstream. They develop pseudopods, and then they pierce the blood vessels and come to the bloodstream. They are carried by the blood, and then they migrate from the bloodstream to go to another organ and sit there. And we do not know, if they sit there, doesn't mean that the cancer will proliferate there. It only proliferates under certain conditions. Again, what I said is not known completely. So then we did proliferation study of HeLa cells. The previous one was mainly mesenchymal stem cells. So we were talking of stem cell proliferation. We were not talking of metastasis. Here we are talking of metastasis, and we found out that the proliferation of HeLa cells due to mechanical forces, two cases we took, one with the fluid shear stress, and along with that, the drug, which is dexorubin, with the standard drug. With that, we found that because the HeLa cells are very common in cancer research, so we wanted to find out what happens with shear stress, with our device, with different shear stresses, and with or without drug, what happens. So we found that number of proliferation cells at 1 Pascal is low compared to other chambers, other values. And the cell detachment at this chamber after 12 hours of flow was seen, and the cell number was comparable in all experimental groups after the drug treatment. So drug could neutralize the effect of this shear stress to some extent. However, when it comes to gene expression, we saw, again, a difference. And the difference is this, that the stemness and migration-specific genes were upgraded with the magnitude of shear exposure. So, with more shear, it is more likely to metastasize. But what is more dangerous is the second one. The upregulation of the gene was higher with the drug-treated cells. That means it has become drug-resistant. Not only drug-resistant, it worsens. The drugs are acting as counterproductive with respect to metastasis. Now, this is very dangerous conclusion. So we have to be extremely careful. Now, the thing is that before coming to the last slide, I will tell that this is the beginning of the story, not the end of the story. Just like in the previous case, we started seeing if we put a thermal gradient and a chemical gradient, how do they interact? Now here, we have put only the pressure gradient. Drug, we have put in everyone the same amount. We didn't create a drug gradient. Drug also, when injected, that will have gradients. In fact, the tumors are the most highly packed cells, and very few things can penetrate. And so you will definitely have a gradient. So what happens when there is a drug gradient and a pressure gradient? Along with that, a temperature gradient, because everybody knows that the hottest portion, if you take a PET scan of a cancer patient, the portion which will be showing as red is the tumor. So all these things, when put together, how do they finally operate? And not only that, along with that, there is an imposed thermal gradient also, which is radiation therapy. You do not give, the way it is done, you give one chemotherapy, wait for a few days, then give a radiation therapy, then wait for a few days, and then again give the next cycle of chemotherapy. What happens? Does the propensity for metastasis increases or decreases with these? Now, you can never do these experiments on human body. It's just impossible. You are not able to see because all the other processes are going on. But if we can create, microfluidic devices like these, where we impose multiple gradients, and the gradients, the way we want, predetermined way of gradients creation, if we can impose on them, then we can study and we can say what is the effect of which one. We can segregate them, we can put them together and understand together with the other ones how they behave. Now with this, I'll come to my last slide. So we can conclude that physical and chemical gradients, such as those of enzyme, drug, temperature, oxygen, pH, fluid flow induced shear stress, and are important for microbial taxis, as well as directed migration of cells in the body. That's the first part of the study. And the second part, it says, with all these, we should be able to develop organ on chip, or even human body on chip, where the proposed gradients are there, and we can see in the laboratory how the gradients act with an organ, between the organs in terms of metastasis and even side effects, and also as a whole, as a system. So this is what we can study in this kind of devices. So novel microfluidic devices is an effective way to study physiology, pathology, and therapeutics associated with directed microbial and cell migration, let it be normal cells or cancer cells. Thank you very much.
Thank you very much for an inspiring talk and all the work you've done now. So I got hung up a little bit on slide 17, I remember the number, and that was where you had the chemical gradients being formed in the gel channel, I think. So my question was, what are the time constants to establish the gradients in those gels? Because it seems like you still have some fair distances to the previous.
This is, if you look at minutes, this is 0, 60 minutes, 120 minutes.
Yeah, and the distances are what?
Oh, distances are distances within our microfluidic device. This device is this much.
Yeah, so I mean the gel channel is maybe a centimeter long?
Yeah, something like that, a centimeter long.
So my question is, to establish a linear gradient or whatever gradient you have in there, what's the time constant? Because then you have a flow-through chamber where you have the cells. And so I just don't see how you match the gradients in the gels versus what you get in the fluid.
We take photographs. How we do it, suppose we are taking, say first let's take, we tested it with say dextran red color. Okay. So we take a photograph and then we do image analysis with the intensity of color. And intensity of color is proportional to concentration. Okay. So with that we find out. Okay. And in case of cells, we count cells.
Yeah. So one more question.
Thank you, Professor Das, for a wonderful talk. I was just wondering that the bacteria, E. coli, do they sense the thermal gradient or actually the viscosity gradient because of thermal gradients?
Actually, that E. coli sense thermal gradient is nothing new. We didn't discover. It's there in literature. They do sense thermal gradient, not very strongly, but they do sense thermal gradient, E. coli. Viscosity, again, I would say viscosity will decide the rate of migration because, it has to swim through that one.
Yeah,
that's what. But thermal gradient, E. coli moving in the direction of thermal gradient is a known information.
Let us give a round of applause to the speaker, Professor Sarit Das, for a very interesting talk. And as a token of appreciation from us,
He has to take the photograph.
yeah.